my OneNote move. I don't know why it doesn't want to move. There we go. Okay, so the plan for today is to first go through a couple of integration practice problems and then start on the topic of approximate integration. I'll have supplements posted in the next day or so um, on partial fractions integration technique and on approximate integration. So 7.4 and 7.7. We have the Unit 1 exam coming up this coming week. So it'll be open a week from today, that Monday at 9 a.m. through that following Sunday. And you can take it anytime during that week. The Examity practice exam has been available for going on a week now. So again, the only purpose for that Examity practice exam is for you to go through the Examity process once, for you to get over to Examity, get the account set up and all of that, learn how it works, get anything fixed up with your computer that you need to. So that's not the exam on WebAssign isn't what's graded by WebAssign, but it doesn't count for a course grade. I didn't really pay particular close attention to whether the couple problems I put on there can easily be completed in 15 minutes or not, right? So it's just to have something in that exam that you can go through the Examity process, get into the exam, do the whole password thing, the Chrome add-on extension kind of stuff, and go through the process once. Now the sample exam for Unit 1 is also posted. So the sample Unit 1 exam here is posted. The purpose of this sample exam, for this one, you do not need to go through Examity. It's not password protected or anything like that. It's also not timed, because if I time it, then that interferes with your ability to retake it. But the sample Unit 1 exam here, the purpose of that is to give you an idea of what's going to be on the actual exam. So the sample Unit 1 exam is quite similar to the actual exam. It's similar in length and the types of problems that are on it and the difficulty of the problems that are on it. So my general recommendation is to study for the exam. When you feel like you're pretty comfortable with the material, then take the sample exam. Use the sample exam as kind of an independent assessment. If you go through and you say, oh, I really didn't do well on problem 6, I really don't understand that material, go back and review that topic. I recommend that you kind of take it in a similar exam setting as to how you take the actual exam. So time yourself, give yourself 1 hour of time, have the resources available that you'll have available for the actual exam. If you treat it kind of like more like a homework or something, and you go through and you go problem by problem and look things up in the book and all of that, that kind of defeats the purpose of the sample exam. That's really more a little closer to the purpose of the homework sets. But yeah, you can take the sample exam as many times as you like. The actual exam will be posted, like I said, Monday 2/19 at 9 a.m. That'll be available. And for that one, you'll have to go through the Examity process, similar to the Examity practice exam, have it enter the password, it opens up the exam for you, and then you'll take that exam, and that will follow those, standard exam instructions. Are there any questions on any of that? So to get to Examity, you just go to the Blackboard site, click the Examity sign on, and then here's some general information about Examity below here, but this Examity sign on link just takes you to where you can launch Examity and get into the Examity system. And from here, you can do whatever you need to do to open up the session. Also, and I forgot to mention it with all the Examity stuff, also in the supplemental resources, I posted an integration techniques practice worksheet. So these are just some integration problems that are separated from the homework sets, right? So in the homework sets, if you know that a problem is from 7.4, you kind of know you need to use partial fractions for it. In this practice worksheet, there's no alignment to sections, so it's not so clear what the right technique to use is. So if you want some practice on integration techniques, these problems range from kind of easy to moderate difficulty to harder difficulty. So you can take a look at this worksheet. We'll work through, in today's class, we'll work through 4 of those problems, these numbers from the review sheet, but there are a bunch of others that you could work through as well. And then we'll start on approximate integration, and again, then have a supplement on the rest of approximate integration. So lots of administrative stuff that I just talked about. Are there any questions on any of that? Okay. So I'll switch my share here and we will get into it. So the first plan for today is to just go through a couple of integration techniques to have you guys actually go through and practice them. We'll take maybe something like 5 minutes each. So for the first one, take 5 minutes, work through it, try to get as far as you can, and then we'll come back together and we'll discuss the solution. We'll move on to the second one and so on. If you finish the first one in under 5 minutes, I'll leave the next 1 or 2 up. You can work ahead if you want to. If you don't quite get finished with one of these in 5 minutes, don't really worry about it. Don't stress too much about it. The 5 minutes is just what I felt was kind of a good amount of time for you to start working on it and to kind of try the problem. But if you don't get all the way to the end in 5 minutes, that's okay. And then probably what I'll do is maybe something like 3 minutes in or so, I'll start writing. Maybe I'll give like a little kind of hint so that if you're really stuck and if you can't figure out a path forward, that hint might kind of unlock you a little bit and you can make some progress before we come back together. So take the next 5 or so minutes, work on this first one, and then we'll come back. We'll discuss it, move on to the second one. We'll do that for these 4, and then we'll move on to approximate integration for the rest of the lecture. So work on this one, 5 minutes or so, we'll touch base again. Oh, and I will have chat open, so if you have any questions, feel free to pop them in chat if you want a hint or something like that, or if you're stuck, you can also pop them in chat and I can answer there. Okay, so again, if you didn't get all the way through everything, that's perfectly fine. I think the real challenge with these problems is really to get kind of that first step or so and get far enough that you see the strategy and that you're able to then carry out the more procedural parts. But the first thing that I notice in a problem like this, I first ask myself, well, I suppose the very first thing I ask myself is this an integrand that I just know what the integral is? And I think the answer here is no. So then I ask myself, what's the most problematic part? What's the most difficult part to deal with? And it's definitely the square root of x in the exponent of the e. I really don't know much about e to the square root of x at all. If I could make that an e to the u, I have a much better shot. So I'd like to start with a simple technique, right? I try to go from simple techniques up to more complex ones. So something like algebraic simplification, just knowing what the integral is, that interpreting it geometrically, that doesn't seem like it's maybe going to be super helpful here, but a basic substitution, u equals root x, might work. Now we might go to du, see that it's 1 over 2 root x dx. I don't see a 1 over root x dx anywhere. And this might give me a little bit of pause, and it probably should. So I might think to myself, like, okay, is there something different that I could do here? Could I do an integration by parts? Well, integrating e to the root x isn't really feasible. Differentiating e to the root x, that seems like it's going to be very messy because I'm going to have to integrate root x and differentiate e to the root x. That just seems very messy. So, I mean, maybe I keep that in my back pocket. Doesn't seem like any kind of trig integral or substitution is going to apply here, or partial fractions. So let's try to push a little harder on this substitution. I do see that, I mean, du is 1 over, basically 1 over root x dx. And that kind of has the feel of root x dx. Can I manufacture a root x dx out of here? Well, sure, if I multiply top and bottom by root x, I can say that this is root x over 2x dx. Well, that gets me the other bit of my integrand. So, I mean, that's a step forward. But what do I do with this 2x on the bottom? Well, I realize that x can be written in terms of u as x equals u squared. Or if I multiply that 2x to the other side, I can do this as an intermediate step. I don't want to plug this back into the integrand as 2x du. That would kind of be bad form. Maybe not so much bad form, but it might lead me to make a mistake more easily. But here I can switch my x into u squared, and I get 2u squared du coming from that root x dx. So after all of this, I get a form of the integrand with an e to the u, which is much more manageable. And my kind of polynomial bit, or my power function bit, is now attached to the piece in front, which is, again, that's going to be a more manageable structure to deal with. And at this point, I should recognize this as an integration by parts problem. Differentiating this guy makes it simpler. Integrating this guy isn't so bad. And I know it's a little silly, but because integration by parts uses u and v, and I don't want to say something like u equals 2u squared, that's going to be confusing. I'm just going to change my variable. I'll just change my variable from u to s. So u is turning into s. I need to remember that at the end when I make my way all the way back up to x. I need to remember that u turned into s, because now I'm going to kind of use u again. I'm not going to end up with u's at the end, but I just need to remember that I did do a substitution here, u equals s and du equals ds. And I just did that for the sole reason. Again, maybe it's a little bit silly, but this is kind of the way that our brains work. I'm used to thinking of integration by parts in terms of u and dv. I would like to keep doing that instead of thinking in terms of like s and dt or something like that, right? So I'll pick u equals 2s squared, the thing I want to differentiate, dv e to the s ds. I've used everything in my integrand, nothing that's not in my integrand. Du is 4s ds, and v is e to the s. So this integral is going to be uv minus integral v du. That made things a little simpler. I want to do integration by parts a second time. And what I'm going to do here is, since I'm doing integration by parts again, I'm going to put this whole -4 inside of the integral. The reason I'm doing that step is because I know from my experience that I could take that -4 times the integral and do the integral and then plug in and distribute the -4. In theory, that works, but in practice, I might be more likely to drop a negative or to just actually forget that distributive step altogether. By sticking the -4 inside the integral, that puts it in the u. I'm much less likely to forget it that way. So now again, I want to differentiate this guy, integrate this guy, copying down that first bit, plus uv, which is a minus 4s e to the s. That -4 gets distributed automatically by the u, so I just don't have to think about doing it in an extra algebraic step. Okay, so I have plus this integral. The integral is uv minus the integral v du. Or this is going to be plus the integral of 4e to the s ds. And a couple more relatively small steps here. And then I have plus 4e to the s. I don't want to forget my plus c, little detail on the end there. And then s would turn into u, and u would turn into root x. So really s turns directly into root x. So here, s turning into root x. So I have 2x e to the root x minus 4 root x e to the root x plus 4 e to the root x plus c. And I could probably factor some stuff out of there, but I think that looks good enough. Okay, so that was, again, a bit of a longer integration problem. I think the crux of the problem, the most difficult part, was that we're naturally led to this substitution. That seems like a good idea. But we seem to be kind of stymied here. And we need to push a little harder to get through to make the substitution work. I think it is a good instinct to say, I'm not so sure this is going to work. Let me look at other options. But any other option didn't seem super appealing. So pushing through here, trying to find a way to make this work. It's not like du was like sine of x dx and I needed to make it square root of x dx. Du was still kind of in the same ballpark as the kind of function that I wanted. So by a little algebraic manipulation, I made it work. And that led me to a straightforward, relatively speaking, relative to the difficulty of the material we're working with, but a straightforward integration by parts problem that we recognize pretty readily, that differentiating this first bit, this power function, makes it simpler, and the exponential as we integrate it gets no worse. So a couple integration by part steps, just being super careful about all the details, gets me the answer. Okay, so This one's up next. Again, take about 5 minutes to work on this. You might not get all the way through it in 5 minutes, but it's really getting those first couple of steps that's really the challenging part. And a lot of the rest tends to be bookkeeping. So another 5 minutes or so, we'll come back and touch base. Okay, the 5 minutes is about up. So the plan for this one is to use partial fractions. We see the denominator factors into a difference of two squares. It's x squared squared minus 4 squared. So it's x squared plus 4 times x squared minus 4. And the x squared minus 4 can factor again into x plus 2, x minus 2. We see we're going to break this one big rational expression into three partial fractions, one with denominator x squared plus 4, one with x plus 2, and one with x minus 2. The x squared plus 4, again, that can't factor anymore, so that's like fundamentally a quadratic bit. The numerator for that one is going to be a linear bit, ax plus b. And the other two are linears on the bottom, so the numerator is going to be just a constant. As an aside, we didn't have anything to simplify here because the degree of the numerator was 0, degree of the denominator was 4, so the degree of the numerator already less than degree of the denominator, so we just jumped right into this step. If we had, say, a 5th degree polynomial up top, we'd have needed to do a little bit of polynomial long division first. Then multiplying through by my denominator tells me that 1 equals all of this stuff, just each of the numerators along with the other denominators that are not under that numerator, the denominators that don't cancel. And we could start by maybe plugging in x equals 0, in other words, aligning the constant terms. So we get 1 equals negative 4b minus 8c plus 8d. That's a little messy. But I do notice that plugging in values like x equals 2 knocks off the first two terms on my right side and leaves me with just the d term. Or x equals negative 2 knocks the first and the third term off my right side and leaves me with just the c term. Maybe I can figure out c and d with that, come back and figure out b with the x equals 0, and then try to figure out something for a. So let me try x equals 2, plugging that in. On the left side, I still have 1. On the right side, this x minus 2 and this x minus 2 knock off that first and second term on the right. The a, b, and c all go away. And I have d times 2 squared plus 4 is 8 times 4. So d is 1 over 32. Let me double check my notes here. That looks good. Plugging in x equals negative 2. Again, x equals negative 2 knocks out the first and the third terms on the right-hand side. So a, b, and d get knocked out. I'm left with just c. So 1 equals c times negative 2 squared plus 4 is 8. Negative 2 minus 2 is minus 4. C is negative 1 over 32. I can take both of these and bring them back up here to the equation with b, c, and d, figure out b. So negative 4b minus 8c over 32, and that's a plus now, and then plus 8 over 32. So I get 1 equals what? Negative 4b plus 16 over 32, so plus 1/2. 1 minus 1/2 is 1/2. Divide through by negative 4. I get b is negative 1/8. That looks good. And now I need to figure out a strategy to find a. I could use a different number like x equals 1 or something. That seems like it's going to be pretty messy, especially with all these fractions. But I might notice that a is the coefficient of x cubed. So maybe I match cubes. I match up coefficients of x cubed on the left and the right. Of course, on the left, the polynomial is just 1, so it has a coefficient of 0 on the x cubed bit. On the right, from the first term, I have an ax cubed. The b at most gets an x squared, so the b doesn't come into play, but I have an a x cubed plus c x cubed plus d x cubed. But nicely enough, c plus d equals 0. So those actually just equal 0, and I find that a has to be 0. So in this case, I did have a linear that I put on here prospectively, but it turned out that I didn't need a whole linear ax plus b. A just turned out to be 0. But I didn't, mess anything up by putting that up there. And in most cases, in most problems, if I didn't have that a term, I would get the wrong answer at the end. But in this case, simplifies a little bit more maybe than usual. So let me zoom out just a tiny bit here. So I see that this integral, the initial integral, is going to be equal to integral of, well, this bit turned out to be 0, so we don't have to worry about that. B is negative 1/8. I'm actually just going to write these as B, C, and D, I think. Because I really don't feel like writing out all these fractions and negatives and maybe forgetting one. So I'm just going to write them this way and then plug them in at the very end. So I see I have 3 integrals here. This one seems a little complicated. Let me revisit that one in a second here. C over x plus 2 is going to be C log absolute x plus 2. And plus d log absolute x minus 2. I'll put something like plus k here for my arbitrary constant. C and d, I'm going to plug in the values in a second here, but for now, I'll just call that constant k. And I probably recognize integral of 1 over x squared plus 4 is something like an arctan, but let's just come over here and work through the details. If I divide top and bottom by 4, on the top, I would get a 1/4. On the bottom, I would get x squared over 4, but that's x over 2 squared plus 1. This looks like arctan x over 2, this integral. If I differentiate arctan x over 2, I get 1 over 1 plus the inside squared, 1 over 1 plus x over 2 squared. That looks good. Chain rule pops out a 1/2. So I need to compensate by making this a 2 over 4 up there to cancel out that 1/2 that would pop out from the chain rule. I could also do a u substitution and so on here. But this is 1/2 arctan x over 2. So this is b over 2 arctan x over 2. And then last thing that I'll do, just plug in my b, c, and d. So negative 1/8 over 2, negative 1/16 of x over 2. Negative 1/16 arctan of x over 2. And then plus c, which was, where was c? Negative 1/32. We'll do it. Minus 1/32 log absolute value of x plus 2. And then d was 1/32 log absolute x minus 2 plus k. I'm not going to worry about combining those logs because even if I did go through the hassle of combining them with the exponents and so on, it's not going to combine with the arctan anyway. So I'll just leave it like this. Any questions on any of this so far? Okay, so on to the next one. I think maybe what we'll do is take 5 minutes for these next two combined and then come back and talk about them. So 5 minutes for the next two combined, and then we'll finish them up. Okay, it's just about 5 minutes. So let's talk about these two. The key insight here is that a to the power b plus c can be simplified as a to the b times a to the c. So we might try some, we might be tempted to jump into something more complicated here. But if we start with just this algebraic simplification, we see that this can be broken down. Now, sometimes we do an algebraic simplification and it doesn't really lead anywhere and we have to rewind and try something else. But in this case, this looks like a candidate for substitution. I might be kind of tempted to start by seeing how greedy I can get. I mean, the e to the x thing is the craziest looking thing. Can I just substitute u equals e to the x? Well, I might actually realize right away that du then is, well, du is going to be e to something times the derivative of that thing. This actually looks like just the integrand here, right? So that actually might clue me into just what the answer is right away. But if I didn't see that, or if I said, okay, looking at this, maybe this is, maybe this seems a little too complex, I could have gone that route and got really greedy and made it work out. That I just got, right, integral of du, and then got my answer. But if I didn't go that route right away, I could at least see that if I pick u equals e to the x, the exponent, then this piece here ends up as an e to the u. And then du is just e to the x dx, everything that's left over. So either route that I took could actually work. This one is maybe slightly more efficient, but you might end up with a structure that you don't quite recognize, where you just end up with an integral du. This one in black here is probably the more kind of standard or more straightforward, more recognizable one, where we end up with integral e to the u du that integrates to e to the u plus c, and then that's e to the x plus c. Either way would have gotten you to the correct solution. And then for the second one, the key here is to realize that the absolute value of a function, well, if that's the integrand, that's really hard to deal with. But I can get rid of those absolute value signs by restricting my region of integration to either the region where the inner function is positive and the absolute values just go away, or the region where the inner function is negative, where I just negate that function. So absolute e to the x minus 1, I've shown the details over here, but this is just e to the x minus 1 for x bigger than or equal to 0. And it's negative of that 1 minus e to the x for x less than 0. I can break this into two definite integrals. And I won't go through the details here, but I think from this point forward, it's not too difficult to carry out. So the key here was, I think of this a little bit like thinking geometrically, just splitting that absolute value operator into kind of its two components. But you might think of it a little differently than that. You might think of it as, say, an algebraic simplification or something, but I think this was a good exercise to go through in class, because this separates out the integration problems from their sections and gives you maybe a little more of a feel of what the problems on the exam might be like when you don't have a section to necessarily correlate them to. And again, on Blackboard, there's a review sheet of 21 problems. And again, some of them are, at kind of the easy to moderate level. Some of them are fairly challenging, and, everything in between. So you can take a look at that review sheet. And then, if you have any questions on particular problems, you can always send me an email. I might try to do a supplement on those as well. So we'll see how time goes this week. Okay, so moving on to just starting 7.7 in the last 10 minutes or so, and then we'll cover most of this in a supplement. approximate integration. So what's the general idea here? Sometimes we have integrals we want to do that are like, say, integral 0 to 1 of x squared dx. Yeah, we can do that all day long. No problem. We can get an exact solution. But sometimes we have integrals like this one. I can't find a nice indefinite integral of e to the minus x squared. So how do I figure out what number this is, right? This is a nice continuous function. This integral certainly exists. It's some real number. It doesn't blow up. It's going to be some value. But I just don't have an easy way to figure out what that value is. So sometimes I'm stuck doing approximate integration, basically using a computer to find the integral for me. There are other times that, maybe I have the integral function that I could in theory do, but maybe it's going to be really annoying to do. So sometimes I, just really can't do the integral and come up with an explicit answer. Sometimes the work to come up with an explicit answer, maybe I could do it, but it's just prohibitively difficult. It's going to take me a lot more time and effort than I'm willing to put into this problem, right? If I'm an engineer designing a bridge, I want to make efficient use of my time, not go through, a 3-hour academic exercise of computing an integral. So these might be situations where I say, okay, I need a certain accuracy for my answer, but I just need the answer. I don't need to understand the thing more fundamentally. I don't need to have a nice analytic solution. So what are some ways that we can get estimates or approximations of the value of these definite integrals? The most basic way is just a Riemann sum. So here I have some function on, say, a to b. And I'm interested in the integral a to b f of x dx. Well, I can just chop my interval from a to b into a bunch of subintervals. We'll say that each subinterval has with delta x. And maybe for the left Riemann sum, above each one of these subintervals, I want to create a box. The box has base at the x-axis. It has the sides, or those two vertical lines on either side. And the height of it I'll set to be the left side function evaluation. I'm going through this a little quickly because I think this is familiar from Calc 1. I know that integral a to b f of x dx represents the signed area under the curve, and I can approximate that by getting the signed area of each of these boxes and adding them together. This would be the formula for that. Alternatively, I could have used the right Riemann sum where I take it for the height reference, the height of the function at the right endpoint of the subinterval. It's qualitatively very similar process. The formula looks pretty similar. It's just a question of, do I use the left endpoint or the right endpoint? Something that's very important to know about an approximation method is what we call the order of the method. So if I say that a method is first order, what I'm saying is if I double n, if I double the number of subintervals, double the number of subintervals, if I double the length of my sum, well, that means I double the number of function evaluations I have to compute on the computer. I can't spell double today for some reason. Double length of the sum, double number of function evaluations. Really what any of these amounts to is I double my work, right? Essentially, I double the length of time that it's going to take the computer to give me an answer back. If I'm willing to put in double the work or double the computational time roughly, what benefit does that get me in the error? It gets me kind of a one-to-one, like a proportionate benefit. Doubling my work cuts my error in half. So n goes to n to 2n, sorry. My error goes to 1/2 of the error. This is what it means to be a first order method. If I were to do 10 times the amount of work, if I increased n by a factor of 10, my error would roughly decrease by a factor of 10. That's not too bad. But if I say wanted to get 4 more decimal places of accuracy than I have now, I would need to do 10 to the 4th or 10,000 times as much work. So, I mean, on one hand, if that goes from like 1 millisecond to what, 10 seconds, did I do that right? If it goes from 1 millisecond to 10 seconds, maybe I'm not too worried about that. If it goes from 1 minute to 10,000 minutes, maybe that's a time scale that I'm not really happy with, right? I want the answer before 10,000 minutes. Maybe I'd be willing to wait 10 seconds, but not 10,000 minutes for the answer. Okay, so one way that I can get more accuracy, get a lower error, in particular, one way that I can, evaluate the yield is by putting in more work. But another way that I can make this higher yield is by saying for the same increment of work, if I double work, can I do some mathematical work? Can I do some background work to come up with more efficient methods so that if I double my work, my error gets cut by more than half? Or if I do 10 times the work, my error gets cut by more than a factor of 10. And that's what these next strategies are. The midpoint rule and the trapezoid rule are called second order or quadratic methods. And Simpson's rule is actually a quartic method. It's a 4th power. For a quadratic method, if I double the work I do, my error decreases by a factor of 4. So n goes to 2n, means error goes to 1/2 squared times the original error. Or if I do 10 times the amount of work, my error gets cut by a factor of 100 for a quadratic method, for a second order method. For a quartic method, for a 4th power method, if I do, say, 10 times the amount of work, my error gets cut by a factor of 10 to the 4th. Right? If I do 10 times the number of subintervals, and in a sense, 10 times the amount of work, I get 4 more decimal places of accuracy. Instead of up here, if I did 10 times the amount of work, I get 1 decimal place of accuracy. I'd have to do something like 10 to the 4th times the amount of work with a Riemann sum to get 4 decimal places of accuracy, 4 more decimal places of accuracy. Where with something like Simpson's rule, I have to do 10 times the amount of work to get 4 more decimal places of accuracy. This is a much better yield. It comes at the cost, it comes with a couple of costs, but one of the costs is the complexity of developing the method. And another cost is the cost of implementing the method. This is a much more annoying sum to implement with all these 1, 4, 2, 4, 2 kind of things than say just a bunch of function evaluations that we're adding up. There are some costs to the higher level methods, but I think people in the field would typically say that Simpson's rule is a pretty good balancing point. You get a lot of nice high yield without a ton of complexity. And if you go much further than Simpson's method or Simpson's rule, then you start to maybe pay a little more in terms of cost than you're really getting in terms of benefit, at least for most applications that most people are interested in and the accuracy that they need for those applications. Okay, so again, we'll kind of go through some more of these details in the supplement, but that finishes us up for today.